All right. Um, Hello, class. Um, this lesson is going to be for the week of May 10th, um, and it is going to be the same lesson for the AP and IB students. So we are going to have three lessons on the topic of fluids. Okay. I like to say fluids in a New York accent whenever I'm teaching about fluids, so I will say fluids, 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 bugger. Hazel just walked out of the room when I yelled fluids. Fluids! I don't know why I like to say it in a New York accent, but I do. All right, so what is a fluid? Well, a fluid it can change its shape. Its shape can change easily. Um, and furthermore, it doesn't really have memory of its previous shape. So, for example, a solid, you can distort a solid, but when you let the solid go, it will shift back, or at least partially back, to its original position. So, fluids, you change the shape, and it's happy to, it doesn't take any effort to maintain that shape, and it'll happily keep that shape forever. Um, so, no memory of previous shape. Okay, so what are the properties of fluids? Um, so so this is like an introductory lesson on fluids. Okay, so we're going to get kind of more technical um, as we get towards the third lesson. But one of the main properties of a fluid is its density, which is denoted by rho. And density is defined as mass per volume. The unit of density is kilograms per cubic meter. All right. Typically, this volume it depends on the shape of the container. Okay, so if this were a cylinder, it would be pi r squared h. If it were a rectangular prism, it would be length times width times height. If it were a sphere, it would be 4/3 pi r cubed. So just whatever the shape of the container is. Okay. Different fluids have different densities. So in particular, you would definitely want to know the density of water. Okay. The density of water is 1,000 kilograms per cubic meter. Okay, so that's really important. All right. The density of salt water is slightly more. Okay. And it depends on the salinity of water, but it is around 1025 kilograms per cubic meter. It's actually interesting. There are so the saltier the water is, the denser it is, right? That's what this equation is saying. And so this actually drives ocean currents, is one of the drivers of ocean current. The other one being temperature. So, if you have water that is really salty encountering water that is less salty, then the saltier water is going to sink below the less salty water. And so, you'll have a downward current that is driven by the salinity gradient as the water slips underneath. Air is also considered a fluid. Okay, its shape can change easily. It has no memory of the previous shape. So air has a density of around 1.2 kilograms per cubic meter. So, these densities are somewhat variable. It depends on the, what is the temperature? Again, what is the composition? But these are just good starting numbers. Okay. Some fluids are incompressible. Okay. Some are compressible. Okay. So incompressible means that the density is approximately constant. Compressible means that the density is not constant. Okay, so now every fluid, when placed under pressure, is going to experience a density change. So that's why I said approximately constant. So really, whether you consider something compressible or incompressible depends on, it just kind of depends on your level of analysis. So a lot of times, for all intents and purposes, the density can be considered constant. So that means that the change in density in the particular situation is so small that it is not significant. Okay. So water, for all intents and purposes, under normal circumstances, can be considered incompressible. Okay. Air, you might think air is compressible, but it's actually, under most circumstances, it is an incompressible fluid. Okay. So I read a textbook on sort of like flight engineering of planes and flight. And flight engineers are, or I guess that's a bad term, but maybe aerospace engineers, I think is a better term, consider the density of air to be constant unless the airplane is going close to the speed of sound. Okay? So, really, the only time that the compressibility of air becomes significant is when you start to get into that supersonic range of speeds. Okay? So, so we are going to be dealing entirely with incompressible fluids, okay? As you can imagine, compressible fluids, the theory is a lot more complicated. All right? So, density is an important property. Another important property is what is called viscosity. Okay. There's a couple of different examples of viscosity, and I always get them mixed up, but sometimes viscosity is referred to by mu, and sometimes it is referred to by nu, the Greek letter nu. and these are different measures of viscosity that are related to each other. One is called dynamic, the other one is called kinematic viscosity. I can't remember which is which. But yeah, there's so anyways, viscosity is basically how thick is the fluid. Okay, so in other words, is it does it slide past itself easily, or does it take a lot of effort to slide one part of the fluid past another part of the fluid? Okay, so kind of how they measure viscosity, all right, is what they do is but this is one way you could measure viscosity, is you make like a sandwich where you have a metal disc, okay, and then you have a fluid, and then you have another metal disc underneath it. So you make like a sandwich, okay. So here's the bottom disc, this, and then what you do is you keep the bottom disc, excuse me, fixed in place, and then you take the top disc and you spin it, okay? And so you have this layer of fluid that's in between, and the bottom of the fluid is not moving, but the top of the fluid is moving, right? Because it's moving with this spinning disc. And so the viscosity is related to how much effort this takes to spin one disc on top of another with a fluid in between, okay? Viscosity is kind of beyond the scope of this course, okay? So we are not going to be discussing viscosity. All right. So the other property of a fluid is pressure. Pressure is denoted by P. And if we think about a fluid, okay, so let's say we have like an ocean, all right, and we had an ocean, all right. Here's the bottom of the ocean. And in that ocean, we have a submarine. So I'm going to represent the submarine just as a box. All right. The walls of that submarine are being pushed on by the fluid. Okay. The fluid wants to fill in empty space. All right. So, you know, the fluid is going to be pushing on the top surface. It's going to be pushing on the bottom surface. It's going to be pushing on the side. So it's pushing on every side of this, okay? All right. And so the pressure is the force on the wall of the submarine divided by the area of the face, okay? So if this face has an area, you know, of length times width, then this area would be length times width, okay? So we could calculate, so that's what the pressure is. You measure the force on this face and divide it by the area of that face. The units of pressure. Pressure is denoted by, well, it's a force divided by an area. So force is measured in newtons. Area is measured in square meters. So pressure is measured in newtons per square meter. All right. This is called the Pascal, which is abbreviated PA. All right. You are probably familiar with the English unit of pressure that is most commonly used, which is PSI, pounds per square inch. Pounds per square inch, right? That's a force. Force is measured in pounds. Area is measured in square inches. Pounds per square inch. That's also a unit of pressure, okay? There is one pressure that you need to know. We don't need to know it, but it's handy to know, which is what is the atmospheric pressure at the surface of the Earth, okay? And it varies depending on weather conditions. You know, you look at a barometer and air pressure goes up, the air pressure goes down. Depends on weather. But it's right around 10 to the 5th pascals. Okay? So that is the air pressure. At this point, I do want to just emphasize P and rho look very similar. So I want to just kind of emphasize the difference between the two. So I'm going to draw the letter like the letters like you're in kindergarten. Okay. So let's say you're in kindergarten. The P for pressure looks like this. It's an uppercase P. This is straight. Rho is kind of like a lowercase p mixed with an E. And it's curvy and it drops below the line. Okay, so that is rho, the Greek letter rho. So don't get confused. Pressure, all right. Pressure varies with location in the fluid. Pressure varies with location in the fluid, okay? Now we're considering very simple situations, all right? You know, so fluid dynamics is a very complicated subject, and actually most problems in fluid dynamics you cannot solve. You just use a computer. So a computer gives you an approximate answer, and you use that to design airplanes, use that to do whatever you need to do. So we're considering very simple applications of fluids, okay? So in general, if you've ever gone swimming before, which I hope all of you have had the chance to go swimming at one point or another in your life, oops, I accidentally clicked something I didn't want to click. Okay. Then you know if you dive down into the ocean as deep as you can go, you can feel the increased pressure on your ears. You can feel that pressure going up. So if you have a static fluid that is still, okay, as the depth increases, pressure goes up, okay? And the reason is that pressure is basically, if we think about a given spot in the ocean, like say right here, pressure is pushing up on all of this water, okay? So there has to be an upward force on all of this water, okay? If there was no upward force, then the water would just accelerate downward under its own weight. So the pressure is holding up all of this column of water, okay? And the deeper you go, the taller that column of water gets, okay? On Earth, air pressure, there is air pressure pushing down on the top of your head, and that comes from the weight of all the air that goes from the top of your head all the way up to outer space, okay? All of that air, the weight of all of that air is pushing down on the top of your head, okay? And it's pushing down with a force of 10 to the 5th newtons per square meter. So there's a nice little equation, which is that the pressure is equal to P0 plus rho g d. Okay, so what do all these variables mean? Well, P naught is the pressure at the surface, which is, of course, going to be atmospheric pressure, okay? You know, the pressure here at the surface is 10 to the 5th pascals, all right? Rho is the density of the fluid. So keep in mind these are two different variables. G is the gravitational field, also known as the acceleration due to gravity. And D is the depth below the surface, okay? And P would be the pressure at that depth. All right. So we can see that as the depth grows, the pressure rises above atmospheric pressure. All right, the pressure at the surface. One thing I want to point out is that, you know, this equation is not just applied to Earth. It can be applied to any astronomical body. So if you were talking about this equation on a different planet, you would have a different acceleration due to gravity, okay? Sometimes planets don't have atmospheres. So if the planet did not have an atmosphere, if there is no atmosphere, then that means that the pressure at the surface is equal to 0, okay? All right, so yeah. All right, and also it's possible that the fluid is not water, for example. Okay, so let's do an example. All right, so let's suppose that you have a submarine, okay? So, and this is Earth, okay? So we're going to use values for Earth, and we're going to assume that this is salt water, okay? And that we have a, well, let me draw some. Got some seaweed. Got some fishies. Fishy is doing a couple of bubbles. Okay. And then we have a submarine. All right. So here's the submarine. The submarine has some windows on it. All right. So the sub has circular window has a circular window of radius, let's see, what would be the size of a submarine's window? Maybe 0.15 meters, okay? And the submarine is at a depth of, let's say, 130 meters, all right? Now, a valid point that can be made about this problem is that the top of the submarine window is less deep than the bottom of the submarine window, so that there's actually a pressure difference between the top and the bottom of the window. All right. But we are going to assume that the window is so small that that pressure difference is insignificant. But if the window did break, you would find, and you can see this in like aquariums, you can find videos of people's fish tanks breaking, and the fish tanks always break from the bottom out. All right, so they don't go like that, they go like that. And the reason is that the pressure at the bottom of the tank is greater than the pressure at the top. So the bottom of the window is being pushed, or the bottom of the glass is being pushed out more than the top of the glass, and so that causes it to swing a certain way. All right. So what I want to know is, what is the force on the window due to the fluid? Okay. So obviously the net force on the window is going to be basically zero, because the structure of the submarine is going to provide an opposite force that is going to hold the window in place. Okay. So what is the force from the fluid pushing in? And then the structure of the submarine provides an outward force that keeps the window from breaking inward. Okay. So first thing I'm going to do is I'm going to find the pressure at that depth. Okay. So the pressure at the top of the fluid is, at the surface, is 10 to the 5th pascals. And again, I am assuming that this is air, okay, or on Earth, okay. If this was in outer space on some planet with no atmosphere, then this would be 0, okay. Plus rho, which is 1,000. Actually, let's use the 1025 because we'll say it's salt water. I did say it's salt water. Times G, which is 10, times the depth, which is 130. So I'm going to plug this into my calculator. Okay. So what I get is 1.43 times 10 to the 6th pascals. All right. Now I'm going to use, so what I didn't ask for is what is the pressure on the window. I asked what is the force on the window. So now I'm going to use the definition of pressure, which is pressure is force per area. Okay. So we can see it has force on the window. So we're going to solve for that. So the pressure I know is 1.43 times 10 to the 6th. The force we're trying to solve for. Okay. And then the area, it is a circular window, so the area of a circle is pi r squared. So I have pi times 0.15 squared. So I can use this to solve for the force. And I get right around 1.01 times 10 to the 5th newtons. So 100,000 newtons is pushing on that window. This is why submarine windows, if you're going to have them at all, need to be really, really strong, because there's a lot of force acting on them. They need to be thick, they need to be small, or you should just not have them, okay? All right, so that is pressure. And the other property that a fluid can have is, of course, velocity. All right, so velocity V, of course, velocity is measuring how fast the fluid is going. Okay, and just like pressure, remember how pressure varies with depth. So it can vary from place to place. The velocity of a fluid can vary. So it will vary from place to place. All right, so the fluid can be headed in one direction at one location, in another direction in another location. It can be going fast in one place, slow in another place. It can be at rest in another place. So, there can be wind here and then no wind someplace else in the world. Okay, so the velocity varies from place to place. And calculating the velocity of the fluid at a given location is basically what fluid dynamics is all about. Okay, we're going to consider a really simple situation of a tube, like a pipe. Okay, and all right, and we are going to assume, so this pipe has a cross-sectional area A. All right, so that would be like pi r squared for this pipe. And we're going to assume that the velocity of the fluid that is going through the pipe is V. All right. And that it's constant throughout the pipe. The fact that it's constant throughout the pipe is not going to be true, okay? Because of, the viscosity of the fluid. So fluids are a little bit sticky. The sides of the pipe will slow the fluid down on the outside. Okay, so the fluid is actually going fastest down the middle of the pipe, and it's going slow on the edges of the pipe. Just like in a river, right? If you're standing next to a river, you can put your feet next to the side. You can stand in the side of a river and not get swept away in it. But if you walk out towards the middle, it's going faster out towards the middle. Same idea. But we're going to assume that it's the same speed throughout, okay? So there is something called the volume flow rate. All right. And it is equal to the cubic meters of fluid per second passing through the pipe, okay? You can also hear it, they often talk about volume flow rate with respect to waterfalls, comparing the sizes of waterfalls. What is the volume flow rate? How many cubic meters of water per second is going over the waterfall? Or rivers, what is the volume flow rate of the Mississippi River? How many cubic meters of water per second are flowing down the river? Okay, so if you want to calculate volume flow rate, all right, it is equal to the area of the pipe times the speed, AV. You can check that it has the right units because area is meters squared, speed is meters per second, so you multiply those two together, you get cubic meters per second. So let's say we had a situation, all right, where we have like a river, okay? So I'm going to try to draw this three-dimensionally. So here's the river. Here's the bottom of the river. Here's the top of the river. Okay, so it's going along. So I'm drawing this three-dimensionally to the best of my ability. Okay, and let's suppose that the bottom of the river comes up. Okay, so it's kind of like this. This is pushing my drawing ability to the limit. Maybe I should have done it like. Man, I messed this up. Okay, well, you get the picture. The bottom of the river comes up. So you have fluid coming in this side. Okay, and then you have fluid traveling through and out the other side. Okay, these speeds will be different. So let's suppose that the width of the river is 15 meters. Okay, and let's suppose that the depth of the river over here is 10 meters. Okay, and the depth of the river here is only 2 meters. Okay, and let's say that the speed of the river at the deeper part is, let's say 0.4 meters per second, so really slow. Okay, and we want to know what is the speed when the depth gets less. Okay, so what is V final? So one of the ideas, there is something called the continuity equation. Okay, and what it says is that for an incompressible fluid, okay, the volume flow rate here going into the river has to be equal to the volume flow rate that's going out. Okay, the number of cubic meters per second going through the deep part of the river has to be equal to the number of cubic meters per second going through the shallow part of the river. Okay, why does this have to be true? Because if it wasn't true, then that would mean that water was disappearing somewhere, and water can't just disappear. All right. There is a version of this equation for compressible fluids, but that's beyond the scope of this course. And so basically what the continuity equation says is A initial V initial equals A final V final. So the initial area would be this area right here, okay, the cross-sectional area. So that's going to be 15 times 10. and the initial speed is 0.4 meters per second. The final area, well, the river is still 15 meters wide, but now it's only 2 meters deep. So it's going to be 15 times 2. And then we want to solve for V final. The 15s cancel out in this case. And so I get 2 meters per second is V final. Okay. So the river, as the river gets shallower, it goes faster. Okay. And so this is actually what is happening when you have river rapids. Okay. The rapids of a river are never the deep part of the river. They're the shallow part of the river, right? You can see the rocks underneath the surface, all that stuff. Okay. So it is a consequence of the continuity equation because the river gets shallower and that makes the river flow faster by the continuity equation. Because the river certainly can't go upward and its surface maintains the same surface level. Another consequence of the continuity equation, you've probably done this before. If you have a hose, okay, so you have a hose, and maybe you're watering some plants, okay, and you put your thumb over the hose, over part of the hose. So maybe you cover up part of it, all right? So now you have, what you have is the same idea here, right? You have fluid that's going slow down the hose, but then the area gets reduced because your thumb is covering part of the hose. And so the water goes really fast out of the part of the hose that is uncovered. And so you can reach plants that are far away. All right. I hope you've had that childhood experience. So that is a consequence of the continuity equation. All right. So that is my lesson for today. There is an associated quiz that I hope you will find very easy. And